Hey everybody, I just wanted to make a short video of the first question on page 22. This is a question that we did together in class on Tuesday, but for those of you that are at home, instead of just looking at the key, it's important that you know how to do these, so I figured I'd walk you through it. There's also one on the homework. These are the types of proofs. I know it doesn't look like the proofs from before, but these are the types of proofs that you're going to see in this chapter. They're called coordinate proofs because you're using a coordinate plane. A lot of times it'll say the use of the graph is optional, but it's so important that you use the graph. All right, so let's see what we got. The vertices of a square are here. Show the diagonals of the square are congruent perpendicular bisectors of each other. So first of all, let's plot these points and see what we're working with. Just remember, this is your x-axis, this is your y-axis. That'll be labeled on the regions. All right, negative 5, 4. So we're going back 5, 2, 3, 4, 5, down 4. And label it with the letter. And do that for each one. So 02, 02 is up there. Now, if you're not sure if it's there or on the x-axis, 2 is in the y position, so you should be marking the 2 on the y-axis. Just a little trick that might help you. All right, positive 6, negative 3, so we're going to go to the right 6, 2, 4, 6, and down 3. Forgot to label this one. And W1, 9, so we're going to the right 1, down 9. All right, now grab something that has a straight edge. If you have a ruler, awesome. It's important that you're accurate with these. Oops, it would help if I grab the right tool. All right, here we go. All right, now this question's telling us to show, and this word show is sometimes replaced with the word prove, that the diagonals are congruent perpendicular bisectors. So first of all, diagonals go from one vertex to the opposite one. So SV is one of them. And the other one is TW. I'm going to actually zoom in a little bit. Okay, so there's 3 things you need to show to prove or show that we're doing this. So you have congruent, so that's your first step. That means that they're the same length. You could use your distance formula. So if you just want to use the points, this is where we'll say, oh, use of the graph is optional. You could just use the distance formula. So if you wanted to find the length, again, you're going to rarely see me use distance, but it's there. It's the square root of x2 minus x1. So you subtract the x values, square them, subtract the y values, and square them, and then add them together and take the square root. Or Pythagorean theorem. Since we have a graph, this is the one I'm going to use. And remember, with Pythagorean theorem, if you have a right triangle, your hypotenuse is across from the right angle, which is your diagonal, and then your 2 legs are your A and B, and those are interchangeable. All right, step 2 is the perpendicular part. You want to show that their slopes are negative reciprocals. So if it's negative 2 over 5, it's positive 5 over 2. And then finally, step 3, you want to show that they bisect each other, which just means they have the same midpoint. Remember, that's when you add your x's and y's and divide by 2. So we add them, and then we'll cut them in half. Okay, so let's get to it. I'll review from previous units, just putting it together. And it's dealing with the diagonals. So we're just looking at SV and TW. All right, so let's take a look at SV first. First thing, to find the length, I'm going to make this into a little triangle. So I'm going to go up 1 over 9. So you count squares. This is 1. If you go all the way over to V, that's 9. I'm going to pull it out here so it's easier to see. So this is 1, this is 9, this is SV. So this is your C. Your diagonal is always your C. All right, so it's going to be, could be 9 squared or 1 squared, it doesn't matter. So 1 squared plus 9 squared equals x squared. All right, if you put that into the calculator, you get 122 equals x squared. Now, if the two sides are 1 and 9, the third side's not going to be 122. So to get rid of the squared, remember we take the square root of both sides. And I'm just going to leave it as radical 122 for now. I don't want to simplify and deal with a fraction. If you want to see what it is to make sure it makes sense, just put it into your calculator. My calculator, I don't think is going to work out. Let's see. Maybe. Not going to get into that. Okay. So let's look at TW. All right, I'm going to switch colors here. All right, so TW goes from up here down to W. So if I make this into a right triangle, I'm going to actually use I'm going to go down 9 and over 1. Change the color of the diagonal so you can see it a little bit better. So again, you're dealing with a right triangle. Might be very slim, but that's awful. There's your right angle, so that's 1, that's 9. And again, your diagonal is always C. The length is always C, your SV. So I've got, and if you're not sure how are you getting 9, how are you getting 1, you're counting squares. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. What did I say? 9? Shoot. These are all 11. Why the number 9's popping in my head? It's probably because it's only 6 o'clock in the morning. All right. That's probably why you were like, well, where are you getting 122 from? You count squares, sorry. So it's 11. All right, so for this one, again, you could either do 1 squared plus 11 squared or 11 squared plus 1 squared. Doesn't matter. Equals your side squared. 121 plus 1 is 122. Take the square root of both sides. And we get the square root of 122 for both. So SV is congruent to TW. And you could just say same length. And your explanation you showed above. Because it'll say, tell whether they're congruent or not and explain. Your explanation is your math. All right, so that's the most work out of these. The rest, you already have your triangles and you've already done the counting. So now it's going to be a little bit easier. So for slopes, remember it's rise over run, and you always go from left to right. So, and I think about it like steps. So for slope of SV, we use a lowercase m, right? So when I want to say the slope of SV, I'm going to put a lowercase m, and then SV is subscript. We're going to be doing a lot of stuff like this throughout the chapter. It's important that you keep yourself organized. So from S to V, we're going, you always start from the left, the point that's furthest to the left, up 1 over 11. And for the slope of TW, again, T is just a little bit further to the left. See how T's at 0 and W's at 1? So to get from T to W, we have to go down 11 over 1. All right, it's always one way to tell you're going on SV, you're going over 11, and I wrote over 11. For TW, I'm going over 1, and I wrote over 1 if you're not sure about how to write those. Okay, since positive 1 over 11 and negative 11 over 1 are negative reciprocals, they're perpendicular, so therefore SV is perpendicular to TW. So there's the first part, here's the second part. The last part, you want to show that their midpoints are the same. That will show this last part that they bisect each other. So let's do SV first. We'll do SV and then we'll do TW. So for this, you can't tell from the graph. So go up and get your points. So SV, -5, -4. And V is 6, -3. Remember, for midpoint, it's like average. So you add them and then cut them in half. All right, because if I just said 1, -7, if I go over 1, down 7, does that look like the midpoint right there? No, you got to cut it in half. So 1 divided by 2 is 0.5 or 1/2. -7 over 2 is -3.5, or you can just leave it as -7/2. And make sure it makes sense on the graph. Over a half would be about here, and down 3.5. Yeah, that looks right. Okay, TW now, grab the 2 points, 0, 2, and 1, -9. And again, add them together. Look at that, same numbers, divide them by 2. And that is also has a midpoint of -1/2, or 1/2 -7 over 2. So your last statement, SV and TW bisect each other because they have the same midpoint. And that is a coordinate proof. And they're going to look all sorts of different ways. Could be, prove it's a square but not a this. Prove it's a rectangle but not a rhombus. Prove it's a parallelogram but not a square. So we'll look at all sorts of different ones like that this chapter. If you have questions, let me know. Have a great day.